Welcome back, students, to the final lecture of physical chemistry. In this lecture, we will briefly investigate some different types of complex reactions that we can relatively easily model and explain. Our focus will be on radical chemistry, but we'll talk a little bit about the end about some oscillating reactions that are pretty fun to watch. The learning goals for today are simply to evaluate complex mechanisms, to validate rate laws like we saw before, and then to just describe some complex reaction mechanisms, to be able to follow through the processes of what we're doing here to be able to predict some rate laws. Radical chemistry involves high energy radicals which have unpaired electrons. We are familiar with radical chemistry from organic chemistry. We've studied these types of reactions. We know that radical reactions begin with an initiation step, continue with propagation steps, and then end in a termination step, some of which are shown here. This example goes through the decomposition of ethane into ethene and a molecule of hydrogen. Here we can see a proposed mechanism for this process. The initiation step is by a molecule of ethane having homolytic bond cleavage into two methane radicals here. And then this radical can steal a hydrogen from another ethane to make an ethane radical. And then the ethane radical can propagate by losing a hydrogen, and then that hydrogen can go and take another hydrogen off of another ethane, regenerating the C2H5. And finally, termination is any number of steps by which we have two radicals coming together to remove the radical. So in the initiation step, we form radicals. In the propagation step, we start with one and end with one. In the termination step, we start with two and end with one. The radicals go away. This mechanism looks pretty complicated. We have 5 steps. We've never seen anything like that before. However, if we follow through the rate law expression, it actually is surprisingly simple. And we come up with a mechanism that has an effective rate constant, but it essentially is first order with respect to the concentration of ethane. So this compares well to the experimental rate law. Also, in this experiment, some very small amounts of methane are also produced, which goes along with that propagation step. So we can go ahead and see how this complicated mechanism actually predicts first order dependence with respect to C2H6. How could we possibly begin to describe the rate of this complex reaction? It's the same as we have ever done. We pick one of the products or the reactants and monitor the change in concentration of that with respect to time. So for this case, we will say that the rate is equal to the negative change in the concentration of our product, C2H6, with respect to time. And then we'll set up the rate law for this, which is how does this change? So we need to find every term in our mechanism that has C2H6, and we can see it is consumed in reaction 1 and reaction 2 and reaction 4, and then produced in reaction 5. So we can set up a rate law for this. We can say that the rate is going to be equal to, first, the reaction based on K1 times the concentration only of C2H6. This is the first reaction. This is how C2H6 is consumed. It's also consumed based on the rate K2 times the concentration of methyl radical times C2H6. It's also consumed based on the rate K4 times the concentration of hydrogen atoms times C2H6. And then it is also produced based on rate 5, and here we have minus K5 times hydrogen atom times C2H5. Now, you may be concerned because our signs are all backwards here. In these first 3 steps, we're consuming, in this one we're making, but we've done plus and then minus. That's because in this case, we're setting this equal to the negative change of C2H6. So if we get rid of that negative, the signs restore themselves to how we expect them to be. To make a sense of this rate law, we must come up with an expression for all of the radical terms. We could easily know the concentration of our starting point, but what about all our radicals? Well, our radicals are intermediates, so we can apply the steady state approximation. Also, in radical reactions, very few radical species are formed. It's a relatively unlikely process. So the steady state approximation is very more applicable than it usually is because we don't really ever get an appreciable concentration of intermediates. So we can say that all of our radical species, their concentration doesn't change, and therefore the change in concentration of our radical species, for example, methyl radical, with respect to time, is equal to 0. So we do that for CH3, we do it for C2H5, and then we'll also do it for hydrogen atoms. And if we do this, we'll be able to figure out what's going on with our rate. So just like before, we can say what happens to the methyl radical over time. The methyl radical here, let's count where it's formed. So the methyl radical is formed in the first step and consumed in the second step. So we can go ahead and plot this here. In order to say that we're forming 2 methyl radicals in the first step, we'll say that we have the formation of methyl radical with respect to time is twice. It's 2K1 times the concentration of C2H6, because every time C2H6 is decomposed, we get twice the amount of methyl radicals. And then we will subtract K2 times the concentration of methyl radical times the concentration of C2H6. Okay, so we set that one up. What about C2H5? Where does C2H5 appear? C2H5 is formed in the second step and the fourth step and consumed in the third and fifth steps. So we can go ahead and write an expression for this. We can say that dC2H5 dt is equal to K2 times the concentration of CH3 times C2H6. And then we will subtract K3 times C2H5. And then we'll add K4 times concentration of hydrogen atoms times C2H6. And then we'll subtract K5 times concentration of hydrogen atoms times C2H5. We'll lastly look for protons, well, or not protons, hydrogen atoms, and we'll find the hydrogen atoms. The hydrogen atom is created in step 3 and consumed in step 4 and 5. So we can say that our change in hydrogen atom concentration with respect to time is equal to K3 times the concentration of C2H5, and then we'll subtract K4 times the concentration of hydrogen atoms times C2H6, and then we'll subtract K5 times the concentration of hydrogen atoms times C2H5. All right, so this, of course, is a pretty easy application of the steady state approximation, but it's still not clear what we do. We can start by pretty easily solving this equation here. All we have to do is add this term over to the other side of the equation. That will give us K2 times CH3 times C2H6 is equal to 2K1 times C2H6. So we can cancel out C2H6, divide by K2, and find that the concentration of methyl radical is simply equal to 2K1 over K2. How do we proceed to solve for the other concentrations of our intermediates? It's not at all obvious, but the best way to do this is actually to sum all 3 of these reactions. Now, what happens if we sum all of these reactions? So what we're going to do is simply come in and sum all of these together. We can do that because each 3 of these equations is equal to 0. So if we add them all together, it's still equal to 0. Now, why would we add them all together? Look what happens if we add them all together. If we add the bottom reaction to this top reaction, we end up having negative K2 times the methyl radical concentration times C2H6 plus positive K2 times the methyl radical concentration times C2H6. So what we can do is simply eliminate these two terms. Then if we add the bottom reaction, we can eliminate this term and this term, and this term and this term, whereas these two will actually stack. So what that will give us when we add these three reactions together is 0 equals 2K1 times the concentration of C2H6 minus 2K5 times the concentration of protons times the concentration of C2H5. We can then add this over to the other side of the equation and rearrange to solve for the concentration of hydrogen atoms to find that the concentration of hydrogen atoms is simply equal to K1 times the concentration of C2H6 over K5 times the concentration of C2H5. With this, we can go ahead and substitute the concentration of hydrogen atom into the equation. So we can substitute this in up here for every instance of the hydrogen atom to solve for for the concentration of C2H5. So what we get is then 0 is equal to K3 times the concentration of C2H5 minus K4, and then we'll substitute in H atom, which is K1 C2H6 over K5 C2H5 times the concentration of C2H6. And then we'll have minus K5, again, times the same thing, K1 C2H6 over K5 C2H5. And here we have the concentration of C2H5. So what happens here is we can multiply it through by C2H5 to remove it from the denominator. So if we multiply each of these terms by C2H5, we end up with the following. We have K3 times the concentration of C2H5 squared minus K4 K1 over K5 times the concentration of C2H6 squared. And then we'll have minus K1 times C2H6 times C2H5. Now, why do we want this? Well, what we can do with this is we can solve it as a quadratic equation. So we have a quadratic equation here with respect to C2H5. So we have one term that is x squared, one term that's x, and this term has no C2H5 dependence. So we can solve this with the quadratic equation to simply obtain the concentration of C2H5 is equal to the concentration of C2H6 times a whole mess of rate constants. We have K1 over 2K3 plus K1 over 2K3 squared plus K1 K4 over K3 K5, and then this whole term is raised to the 1/2. All right, this is pretty gross, but what we can do is appreciate the following. Each one of these terms depends on K1. Going back to the original scheme, we see that K1 is the rate of the initiation process for this reaction. Going back to what you learned about radical chemistry in organic chemistry, you know that initiation is a relatively unlikely event. Not very many molecules actually decompose. Now, what that means is that initiation is slow and K1 is very small. If K1 is very small, then the K1 squared term here is even smaller. And if K1 is small, the square root of K1 shown here is much bigger than K1. So with that, we can say that this term is the only one that is actually substantial to measure. And if you don't believe me, you can go take a small number. You could say take 0.00, let's do another 0.0001 plus 0.0001 squared plus 0.0001 raised to the 1/2. This would give me 0.0001 plus 0.000001 plus 0.01. So clearly this is far and away the biggest term and the only one that's going to matter overall. So with that, we can say that this whole thing is approximately simply the square root of K1, K4 over K3, K5 times the concentration of C2H6. We can then solve for the concentration of hydrogen atoms. So the concentration of hydrogen atoms is equal to K1 over K5 times C2H6 over C2H5. And now we know what C2H5 is, we can plug that in to find that the concentration of protons is simply equal to K1, K3 over K4, K5. And take the square root of those. Plugging these all back into the expression for the rate allows us to actually solve for the rate. So what we're going to do is simply take our expression for the rate, this original one. I'll copy it and bring it down. So we can copy this expression. And we have now solved for the methyl radical concentration, we've solved for the hydrogen concentration, and we've solved for the C2H5. So with this, we can say that the rate is equal to K1 times C2H6 plus K2. Now for the methyl radical, we said that was equal to 2K1 over K2. So we can say 2K1 over K2 times the concentration of C2H6 plus K4. Now we've solved for hydrogen. We know that hydrogen is K1, K3 over K4, K5, square root of that, times C2H6 minus K5. We have hydrogen again, so hydrogen is again K1, K3 over K4, K5. And then C2H5 is equal to K1, K4 over K3, K5. With this, we can go ahead and factor out the C2H6 and actually solve for what this rate is. So if we take out C2H6, what we're left with is from the first term, we're left with K1. Then we're left with 2K1. In the third term, we are left with K1, K3, K4 over K5. And then in the second, what's going to happen here is the K1s will add up, the K3s will cancel, the K4s will cancel, the K5s will cancel with this, and so we'll simply have minus K1. So putting all of this together, we will end up with 2K1 plus the square root of our rates. Using the same approximation before, we'll say that this one will be by far the largest since K1 is a small number. To approximate the rate as K1, K3, K4 over K5, take the square root, and multiply by C2H6. So experimentally, we would measure some number that we could describe as the product of all of these rates here, but we would measure first order dependence with respect to the concentration of our reactants. Most radical chain reactions, no matter how complex the mechanism, are either first order dependent like this, or sometimes they're second order or even 1/2, 3/2 order reactions. We can also apply a similar mechanism for radical chain polymerization reactions. The difference here is that in a radical chain polymerization, you get longer and longer polymers as a function of reaction, not just changing from one molecule to another. A general mechanism can be shown here, where there's an initiator molecule that decomposes into two radicals. The radical propagates with a monomer to make a radical monomer that then hits more and more and more monomers, making larger and larger and larger monomers, all at the same rate. And finally, we get termination when two of those radical monomer chains come together to get a final non-radical polymer. We can describe this essentially the same way we've done before. Using the steady state approximation, we can say that the rate of change of our reactant species is not changing with respect to time. So we can set up the way that this is formed based on the initiator and is consumed based on termination to come up with an equation that's a 1/2 order dependence based on the initiator concentration. And then we can plug that into our rate law where our reaction rate changes with respect to time. And this is an experimentally measurable rate. So for these kind of radical chain polymerization reactants, they depend 1/2 order based on the initiator concentration and 1st order based on the monomer concentration. So this mechanism that we know from things like organic chemistry actually explains the experimentally predicted rate law. Something else that we can do that's actually rather interesting is take this here. This nu is the expected number of monomers in the polymer chain that we would get. And we can describe this by simply taking the rate of monomer extension over the rate of monomer formation. So you'll get as long as a chain based on how fast extension is compared to how many chains you initiate. And if we go through and use the definitions here come up for by the rate, we can get an expression based on concentration of monomer and initiator for how long we expect the radical chains to be. Another interesting thing we can explore is explosions. An explosion occurs with a kind of interesting chemical reaction where the reaction gets faster with time. Now, typically, we've been talking about reactions that slow down as a function of time because we say run out of reactants as the time goes on. However, for explosions, and we've seen explosions in the lab and demos, things where like a hydrogen balloon, where that balloon pops, you get a big explosion of fire. These kind of reactions actually increase their rate with respect to time, such they lead to an explosion. An example for why explosions would happen can be shown here in a branching reaction. A branching reaction is a radical reaction whereby we have a formation of radical, but then there is a branching step where that radical branches into a phi number of radicals, so more than one radicals. If you have an increasing number of radicals, you will have a faster reaction as more reactions happen with more radicals. So this has been proposed in the hydrogen atom or hydrogen molecule exploding with oxygen, that there's a branching step in that process. Eventually, there's termination where the radicals go into some other product and losing the radicals. Just like we've always done, we can describe the rate of this process as is shown here. So the rate of our concentration of radicals are formed in the initiation step and consumed in the branching step and the termination step. So we can pool all of these together to get an equation that looks like this, where the gamma is substituting in for this term, so based on the initiation, and then the K effective is all of this here. It's KB times phi minus 1 minus KT. We do it in this way because we can see if there's a difference between the termination and the branching rates, we get very different results. So if termination is much faster than the branching rate times the number of branchings minus 1, what we end up with is an equation that looks like this. So gamma, which is, remember, our ki times a over b over kt, and then 1 minus e to the minus kt. So in this case, the rate with respect to time will decrease based on kt. So this is saying that termination is faster than the branching. So we're more likely to terminate. We're not very likely to get a branching reaction, and our reaction slows down, and we get less radical over time. However, if the branching is much greater than the termination, what happens is branching dominates. Our concentration of reaction is equal to E raised to the positive number. So the concentration of our intermediate increases with time, and we get explosions. Lastly, I want to briefly mention the case of oscillating reactions. Oscillating reactions demonstrate periodic changes in concentration with respect to space or time. An example of this is the Belousov-Zhabotinsky reaction. And I'll go ahead and show a video of this here. So this is an example of the reaction that I just mentioned, and we can see it is pretty funky. Your book has an image of this, but I think the video does a little bit better job showing what's going on. In this particular reaction, there is a color change, but you can see that color change is not uniform. We get these wave patterns. So what's happening here is the concentration of the reactant intermediates actually vary as a function of space and time, which allows these wave fronts as the concentration of the intermediates changes. So how can we describe these types of reactions? This reaction demonstrates what's called quadratic autocatalysis. So what's meant by quadratic autocatalysis is we can see here in this mechanism. This is the mechanism of the reaction that we just observed. So we have bromate anions reacting with HBrO2 and protons to make 2 BrO2 radicals and water. And then the BrO2 radical reacts with a cerium 3+ to oxidize that to 4+ and make an HBrO2. So the net reaction here involves 1 molecule of HBrO2 making 2 molecules of HBrO2. Since in this first reaction, 1 molecule makes 2 of these radicals, so we'll get 2 of the second step for every 1 of the first step. So we actually have a 1 molecule making more of itself. This is the hallmark of quadratic autocatalysis. With this, we get a reaction rate that actually varies in time. Initially, this reaction will increase the rate of reaction as we make more of one of our reactants, but then we'll consume products and actually slow the reaction. So we get a change with concentration of these intermediates with respect to space, which gives us these wave patterns that we see. We can describe this just like we have done before to come up with an expression for this that is actually consistent with the rate law. It's pretty complicated and uses the pre-equilibrium assumption based on the fact that this second step, this oxidation of cerium, is pretty slow, but this allows us to, again, establish that our rate laws are working. The final reaction rate has a half-order dependence with respect to HBrO2 and bromate, but it also has a 3/2 order dependence with respect to proton concentration and a first-order dependence with respect to cerium plus. With that, we can conclude this chapter and also the whole semester. So the focus for this chapter is basically these complex mechanisms are simply mechanisms with multiple reaction steps. And we can usually, at least for some simple reactions, boil them down into relatively simple rate laws to validate the mechanisms. So the mechanisms are consistent with the experimentally observed rate laws, even though the mechanisms are complex. that gives us ability to trust in these mechanisms as actually being the way by which these reactions proceed.